Hello, and welcome to the next segment 5 of video training overview of hyperspectral imaging technology. In this presentation, I will go over practical aspects of Pushbroom hyperspectral imaging. Practical aspect of Pushbroom hyperspectral imaging. Look at the lens, focal length, field of view, resolution, focus, depth of field, sensor exposure time, sensor frame rate to achieve square spatial pixel. Look at white and dark reference, white reference height. Here we have a lens parameters. Focal length is a fixed per lens. Shorter focal length is the wider field of view. Lens f number will be set to 2.0 for hyperspec vernier, and 2.5 for nano and micro hyperspec. F number equals focal length and diameter of lens. Smaller f number, wider aperture opening. Smaller f number, shallower depth of field of view. Focus. Here we have a field of view. The FOV dependent on focal length of lens, slit height, focal plane array size. Here we have field of view and spatial resolutions. You can see the top picture there, that frame rate correct for square IFOV. And the bottom we got frame rate too slow. So spatial resolution and slit direction dependent on focal plane resolution, pixel pitch, number of pixels, the field of view. So spatial resolution and travel direction depend on travel speed, slit width, 1 to 3 pixel, Y depending on throughput requirements, detector integration time, or frame rate. Here we have the spectral sampling interval versus the spectral resolutions. So the SSI parameter is related to geometric spacing, dispersion, etc. Optical spectral resolution is usually broader than SSI. Example, like 20 micrometer slit and 6.5 micrometer. Pixel pitch with equal slit is approximately 3. The pixel Y spectral resolution 3 times SSI plus a little more because of other factors. Here's the sensor exposure time and frame rate. Sensor exposure time per frame, typically in millisecond to 10 second of millisecond. Exposure time chosen to maximize signal but avoid detector saturation. Longer exposure time needed for low light sensitivity. Too long exposure time can result in large dark current. Usually not an issue with the SCMOS sensors. Scan speed chosen to achieve square pixel, depending on IFOV and frame period. Here we have the illumination source angle, typically sensor downward looking, light source at an angle. Diagram, the left hand side, you can see it's a correct sample height. The right hand side shows the wrong sample height. Working with 3D samples, Narrow light source at an angle does not illuminate surface sensor is looking. Need to broaden light beam to cover 3D height variation. It's also a trade-off on light concentration and intensity. Lens focus may be an issue. Narrow down on aperture to increase depth of field. Look at the diagram on the left. You see the the sample incorrectly illuminated, and on the right is the 3D sample illuminated with broad beam. Unwanted light exposure and sample heating from illumination source. Sample heating may occur, light intensity too high, excessive exposure time, scan rate too slow. Spectral filter at light source may help reduce unwanted wavelengths of light. Head walls, light source have filter holder at exit of light bulbs. This shows about half solar radiation is in the near. The other half is mostly in the visible and about 5% in the UV. The amount of energy in the MVIR and LVIR is a very small percentage of the total energy from the sun. System performance modeling is helpful in determining which system to buy and what are the limits of operating conditions. For example, can't fly too fast because sensor requires a minimum integration time for sufficient signal, especially when the ground reflectance is low. ModTran is by far the most commonly used program to generate models of radiant based on numerous atmospheric condition, time, location, etc. Headwall has models of the system we sell from full optic to focal plane output with very good accuracy compared to measured results. We can provide models of how our system will perform under different flying conditions. Here we have the Earth's surface albedo. So on the reflectance from chart, water is a low reflectance, fresh snow, high reflectance. On SNR, bullet, amount of light arriving at the focal plane and focal plane efficiency contribute to signal portion of SNR. Focal plane electronic noise and vibration, especially on rotorcraft application, contribute to noise portion of SNR. White, gray, and dark reference. White reference correct for non-flatness of illumination spectral shape, illumination non-uniformity. Spectron, white diffuse reflectance standard, very flat spectral reflectance. Scan white reference before sample scan. White reference should be at same illumination height to mimic what sample sees. Dark reference to subtract sensor dark current. Gray reference used when samples are dark. Allow using brighter illumination. Wider lens aperture no longer exposure time without saturating white reference scan. This will conclude presentations. Stay tuned for next segment 6 overview of hyperspectral imaging technology. Thank you for watching.